Recording in progress.
Okay, cool. Okay. Actually, before that, I want to talk about something else, which is the study system. How did you guys find it last week? Good. So what was like the big, actually, let's go to the class. What was the big change you made compared to last week? At least, because it will be slightly different for all of you. Do you want to go first, Iman? It's not a big, like whatever change you made compared to before.
Probably like the comparing part, like seeing what I did wrong. Like I added that in, like I took more time into that.
Yeah. And how do you sort of do that part?
Like after I attempted the question and like tried to figure out what was wrong, I went through the solutions and then I figured out what I did wrong and what I did right.
Okay, that's pretty good. That's an improvement from before, right? Because were you referring to solutions before?
Oh, yeah.
Oh, so what's it like the improvement now compared to before?
Like I actually spent more time on the question instead of like getting it wrong and just going straight to the solution.
Ah, yes. Okay. Yeah. So you spend time before you went to solutions. Okay. That's a great starting point. Right? That's actually like probably one of the first things we're going to improve in that first stage, which is the practice question stage. Right? Which is what you used to do, but we want to upgrade that bit as well. So you made an upgrade here. That's good. And then we've also got the cycle, which is identify the learning gaps. And then learn it, which is with the trickier one. So we didn't work on that as much last week. So the reason we want to spend more time here is because if we take a look at the answer, we lose all of the like potential benefits we get from retrieving and generating that answer, right? That's where the learning happens. You remember what you do, right? Like, for example, like, let's say you're learning a new board game. Like last week I was learning a new board game. It's called, what was it? I haven't used the name that much, so I can't remember it. Give me a second. I need to know this. Oh yeah, it was called Heat. It's like a board game where you go around like a little toy car basically, but with it's like a die base, it's like Catan, Monopoly, that sort of thing, but the new version of that. And we spent like an hour watching YouTube tutorials with my friends to figure out how to play it. But we didn't get very far. But then I tried to just start playing the game with my friends, and we learned most of the rules in like 20 minutes. Why? Because we used that knowledge, right? We apply the rules to the game. By applying it, we learned it, right? So it's not just like learning everything we like. Sorry, not just school, but everything we learn. If we apply it, we learn it, right? So for the homework we do, by trying to generate and apply it to ourselves, we also get that exact same benefit, right? So like it's not just like your brain doesn't change its process all of a sudden when you're studying. Your brain wants to study in the way it wants to study, which is applying it to something. So you want to replicate that. And that's why spending a bit more time to like try to apply the knowledge is really good. So that's a great step. Kamal, what about you, Akshadi?
Pretty much the same as him, but I think I also, instead of just going like straight to the solutions, I kind of like if I struggled in a question, I used ChatGPT so I could see the like how they worked it out. So I could, not for the answer, but like just so I could see how they worked it out. And then I did the question, and then on a separate piece of paper, I kind of like wrote my own examples and
that's great.
Practicing them.
So that's like you've done this bit as well a bit, right? So again, relearning is hard. So you got a bit of help from ChatGPT. That's great to start off with. But once you relearn something, you reapplied it. is super important because whenever we have a weakness, that's something our brain's going to forget easily. So you should reapply it so that you're going to be less likely to forget it. Cool. And what about you, Nathika? What sort of changes?
For the practice questions, I did more recalling, so like not referring to my notes.
Yeah, great. That's the foundation, right? Recall is the foundation, and then we build on that, right? So I think I'm going to try to sort of give you small little incremental improvement for next time as well, for the holiday homework as well. So one thing you can do to really improve the recall even more is instead of your goal being to create just the answer, just to find the answer, you want to be able to make it to write a solution. And this is this is really good because you're doing a lot more recall in this. You just basically double your recall. Now, the reason a solution is better than an answer. So let's say you have a question. Actually, first, let's define like what a solution is compared to an answer. So if you go to a pretty easy question, let me take a look at a question from the homework. Where's the homework sheet? Okay, so the question was, okay, yeah. So the reason this is good is when you do this, you not only get to recall more, you also get to identify more learning gaps. So here's what I mean. For example, let's say for question J, 59 times 159 mod 6. Let's say you just did, this is going to be 5 times, you did all the things on the side, basically. You did, let's say you do all your calculations, you've done them, and you quickly do this, write them out. Right. Pretend you did the calculations, basically. And when you do this, you end up just quickly putting the answer as well. So let's say it's 3 mod 6. You know everything here. Pretend you've done the calculations. Nothing wrong with it. But you lose the generation effect because you don't organize your effects as answer as clearly as you would in a solution. So the solution, how it would change is this. 59 times 159 mod 6. You want to explain yourself. You want to say, we want to find the residues of 59 and 159 in mod 6. So you're explaining your steps, and then you go, oh, well, by long division or something. Whatever division method you use. Which are the working after that in a clear place here. So you get, you don't need working after this one, but let's say we did. I did it. 5, 15 goes into 2 times. So your remainders are 3 and 5. So you find your remainders and you say, therefore, 59 is congruent to 5 mod 6. And 26 is congruent to, 156. No, 159 is congruent to 3 mod 6. I'm just really justifying every step in the process. And then you have to make sure that because it's the solution, you have to make sure every step is logical. Like pretend you're the teacher making the solution. You're making every step logically consistent. And then in your brain, that logic will build as well. If you just do it this way, it's sort of all over the place. Because you'll have your calculations on the side somewhere, things over here. But if you do it like this, you also really need to organize your thoughts. So you need to put it into words. That's another bit of recall. You're doing recall there, converting the idea you have into words rather than just the symbols. That's recall. But then you also need to, so you get extra recall here. And sometimes you could like find more gaps. And what I mean by that is you also then say, we can then replace 59 and 159 by their residues, which is the multiplication property. Remember? But then you might like, at this point, you might be like, oh, but I don't remember why the multiplication property works. You might ask why on the side, like make it a learning gap, right? And then you can ask ChatGPT afterwards why it works, why it is true. Because I've had this happen a lot. I remember like what the process is, but I don't know why the process works. In that case, good to ask ChatGPT or whatever resource to get help. And then after that, you can go, oh, 59 times 159 is congruent to what? 5 times 3. Just replace it directly. And then like, now it's a solution, but you don't need to go over like basic things like multiplication, right? Just quickly, 15 mod 6, which is 3 mod 6. Like you don't need to explain that. That's pretty obvious, right? If it's not obvious to you though, obvious is different for everyone, depending on what stage you're at. If this step feels tricky, that is a good time to explain it. Any step that feels major, you should explain, right? So by doing the solution, you have to organize your thoughts so you have much more clarity about how you're meant to do it, like a sequence of things. Second, you also have more recall because you have to convert the thoughts in your brain, not just into the algebraic symbols, but also into words and explain it to people. And that's something called interleaving, where you think about the concept in multiple ways. Here, you just think about it symbolically in algebra, numbers. Here, you think about it symbolically, but also in words, and try to do that. Now, it's longer. It's a bit of a longer process. Look at the same question, 3 lines versus like half a page. So it's going to be hard for you to do for every question, but whenever you see a question that's like sort of newish and you haven't seen much before, try to do the solution for this, and like you'll get a lot of benefits from that. And in the long run, it's more worth your time. You'll learn more in a shorter time period by doing this. So you'll get through less questions, but in those less questions, you'll learn more. Does that make sense? So this is a way you can upgrade at this stage, right? So I think that's probably the biggest thing you can work on for now. Work on this stage. I think that's a good fix for all of you because all of you are doing the basics at this point, which is really good. You're all doing recall. You're all trying to slowly sort of incorporate more, like to like sort of stick with the question for a bit longer, which is important, right? Like, of course, if you're completely stuck, and you have no ideas, then that's fine. But if you have ideas but it's just hard, do not give up. Just stick with it for a bit longer, and then over time you'll build your like ability to stick with problems for longer. Cool. So the full solution like this is really beneficial for you. Try to give it a go for your homework, and yeah, any questions about that? No. All right, I'm gonna take a photo of this, put it on the Discord as well for you guys. In the meantime, let's work on some exponential questions. For exponentials, the property is very similar to the multiplication property. So multiplication property is this: if A is congruent to B mod C, and C is congruent to D mod, not C, N here. What does that mean? If you multiply A and C, they're congruent to B and D. Why? You don't have to give the full explanation, but like the intuitive explanation. It's a substitution, right? You're replacing A with something congruent to it, and you're replacing C with something congruent to it, which is D. And so it's the one-to-one replacement essentially with things that are the same under the congruence. Now the proof for that is a little messy, so we won't get into that. But you can use the algebraic definition for the proof. So it's not super easy, but if you use the algebraic definition, which is if A is congruent to B, A minus B is a multiple of N. If you use that definition, you'll figure it out. And next thing is, sorry, yeah. So the power property comes very similar to that. It just says A to the K is congruent to B to the K, mod N. And the idea is literally the exact same. It's a one-to-one substitution. How many A's do you have on the left being multiplied together? K lots of A, right? You have K lots and you have K lots of B here. All you're doing is a one-to-one swap of each A with something congruent to it, because we know that A is congruent to B. That's one of these assumptions. You just swap it one at a time. And when you do those K swaps, you'll get from A to the K to the B to the K. And another thing is, most questions won't give you that second number. So where do you get that second number from? Any ideas? It's very similar to what we saw in previous question. A lot of ideas repeat itself. Where did we get the second numbers from in like this solution, in the multiplication question? We got 59 goes to what? 59 goes to? Yeah, the remainder or the residue. So the residue is always probably one of the best starting points. Now, it's not always the answer, because for the powers, there is another trick where we go beyond the remainder, but it works most of the time. So good starting point, remainder. So for example, if I ask you, what's 7 to the 100 in mod 6? What can you replace 7 with, according to this rule? What's the residue of 7 in mod 6?
What's the remainder? The
Yep.
residue 1.
Yeah, 1. So you can just replace 7 with 1. And what's 1 to the 100? 1. That's special. It's always going to be like 1 or negative 1 in most cases. So it's 1, it's the remainder. So this is congruent to 1. That means when you divide 7 to the 100 by 6, the remainder will be 1. So that's usually the trick.
Would it be 7 divided by 6 or 6 divided by 7?
7 divided by 6. You're always dividing by n, whatever the mod is. Because that's the definition of mod. Like it's saying, what's the remainder when I divide by n? And then another trick is the opposite way, which is, let's say 11 to the 100 mod 6. What's the residue here?
5.
Yep, 5. So it's 5 to the 100. But is this nice? Can you guys calculate this? Give me 5 seconds. It's impossible, right? It doesn't matter if I give you 100 seconds or if I give you like a couple hours, probably won't get it. I won't get it. Will it work with the calculator? Maybe. I think this is calculatable, yeah. But then it won't give you all the digits. Calculator's like 10 digits only on the screen. This has like 30 probably. So it won't give you everything. Sorry, let me see. So even this is too big at the moment, right? So how do we make it approachable? Yep, but this is the residue already.
Oh.
Yeah, that's the problem. You got to the residue. There's a little trick. This is a trick, right? In that we can invoke negative mods if needed. And the way we get to negative mods is by using the property. If two things are congruent, they're different. In mod 6, their difference is a multiple if. Do you remember the property? The definition, sorry. If two things are congruent, their difference is multiple if 6. So if you subtract 6 from 5, you'll get to a number congruent in mod 6. So 5 is congruent to what? Negative 1. Look, the difference is to 6. So they're congruent. That means this is also means 5 to the 100 is congruent to negative 1 to the 100. Mod 6. And that's going to be close. It's an even power. Positive. So evens will count. If it's even power, the negatives will cancel out. So you end up with a positive 1. Mod 6. So sometimes you might need to go down to the negatives. Cool. Any questions about that? No. All right. In that case, I'll give you a couple questions to do. We'll just do like some of the questions again. So one of the questions is we can do part L here, part K and part L. Yep. If you want, I can do it. If you have homework,
Yep.
can you do it on another one? So that I can.
My book after. Or do you want me to give you?
What do you prefer? You mind using this for now then?
Yes.
Just for this session. But that's it. Still upload the homework afterwards as well for you, Nathika, because you get extra feedback then. It'll be like a more quick. If you have any questions, let me know. I know I'm marking, but I'm happy to come. And I know some of you have already done the question, but do it in the sort of the new methodology that we maybe you might have not have done in the previous homework. I have realized I probably only have time to go through question one. So I've gone through question one for all of you. For you guys. Yeah. But I'll take a look at the rest of it of the class. Okay. I realize it's gonna take a little while otherwise, but so you're on the right track. You find the residue, but that's still too big, right?
Yeah.
Come with another potential number we could use instead of the residue.
Negatives. So I have to do would be 6. 6 take away 5 or 5 take away 6.
What do you think? Guess.
5. Yeah. Oh. Is 5 take away 6 would be a negative? No. So
Ah, cool. But thing is, remainder, right? For your one, you've done everything right here. And then you get to -1. But can the remainder be -1? You divide two positive numbers. What's -1 congruent to in mod 6? Okay, you can leave it as -1 if it's just the congruence, but if you go for the remainder, like you're correct till here. But if I asked you what's the remainder when I divide this number by 6, what's that? 5? Yeah. You'd go back up to the positive. How do you do that? By adding 6. Yeah. If they ask you for the residue modulo 6, or just the remainder when you divide by 6, you don't want to leave it as -1.
So that's only if it's a negative number.
You always want to just the remainder. So if the number's like 14,
Yeah.
you want to bring it down to 2. Whatever number you get, you bring it down to like between 0 and 5. Make it like possible to be a remainder. If it's -10, you'd bring it up twice, because bring it up 1 to -4 is not enough. -10 would go up to what? 2, because you had 12. So you just make it so that it fits between 0 and 5 essentially. Or it would change between, like, if n is like 10, it's between 0 and 9. As long as it's less than 10 and positive. And non-negative, sorry. Cool. So you guys look good. Let me take a look. Yeah. Well done. And you justifying the step. Yeah. All right. Cool. Do one. All right. So does that make sense for the exponent ones? They're not too hard once you get the trick. It's just the initial, like the trick itself is kind of weird. So once you get a bit used to it, it's not bad. All right. Any final questions about that? All right, in that case, it's only been 40 minutes. So we can keep going. Let's just do one challenge problem, and then we'll start the new topic. So that trick of like -1 and 1, it doesn't work all the time. It works a lot of the time, but it doesn't work all the time. We'll see like an example where, oh, no, wrong one. But we have to use a different trick. Sorry, same trick, but we're using it in a different context. And we won't simplify it down to 1 or -1 this time because we can't. This is the question we're going to do. Find the remainder when 9 to the 42 minus 5 to the 42 is divided by 7. So they want you to find, essentially, another way to put this is find the residue of 9 to the 42 minus 5 to the 42 mod 7. Cool. So oh, by the way, just a quick tip for the solution method, because I see that you guys are being more detailed with the solution thing. Very good. But you don't have to do this in a test. You just when you're learning at home or like doing homework, you can exaggerate the steps, do more than needed. But then in the test, because of time pressure, you can turn it back down to what you normally do a bit as well. Right? So this is just at home, you get more learning by doing this, but don't try to do it always at a test. You can, take shortcuts a bit more in the test. Because they're looking for an answer there in the test, not a solution. Okay, anyway, back to the problem. We have 9 to the 42 minus 5 to the 42. Oh, yeah, by the way, I've realized I didn't put solutions up for this. I'll put the solutions up. Oh, wait, no, there is no solutions on this book. This is hard in the sense that it's more open-ended. This is what a hard question is. It's like when you take a look at the solution, it'll make sense. But you know what makes this question hard? You're combining a few of the concepts together. It's not just one single concept here. And persevering through this problem is where you're going to get more benefit. Oh, you're doing difference of vector squares? That works when it's just like the two. Just like this. So this rule applies for squares. Not to the power of square, not to a big power.
Oh,
So if it's 9 squared minus 5 squared,
yeah.
that wouldn't be the case. But it's too big for that, unfortunately. Good try though. We do, but to be fair, we're going to use that property soon. Now in quadratics.
Yep.
Cool. Yeah. Try. Think about what other concepts we can use. Think about some other relating back to some of the problems we've solved here. Reducing the down in the mod.
Did the perfect square thing.
Oh, okay.
Yeah, but I think I know what to do. So cool.
Next section.
Is there a shortcut to this, or do we just have to?
No, you don't need to compute it, but there's something you can observe about this that will make it so that you don't need to calculate anything. Why do you think that is?
because it's got the same like power,
Yes,
so you can not just straight minus it.
sort of the same power, but like, what else is about this? The thing is, this is the same base, right? Essentially,
Yeah.
2 and -2, but if this was odd, would it work?
Like if these were odd.
If the powers were odd, sorry.
Oh, no.
Why not?
Oh, because this would be a positive,
Other way,
or this would be a negative.
this will be negative, and this will still be positive because 2 to the 41 is still going to be, let's say it's 41 instead of 42.
Hmm.
2 to the 41 is positive, -2.
Oh, yeah.
So you're subtracting a positive from the negative. So when you minus the negative, it adds. So what?
Oh,
But because it's even, negative doesn't matter in this. Equal the same thing.
Yeah.
Subtract it. That's why, like, that's why you should try to represent it as a solution, not 0 to the 42. This is just say, technically yes, 0 to 42, but it's just 0
this is, yeah.
because they're the same number.
This part you can for the residue of 9 to the power 42 and what's that? It would be that. Right? But then would you leave the 5 as it is?
You would if you can do something there. Can you do anything there?
Sure.
Like, can you move forward with any other properties we can use here? Basically, our goal is to get numbers we can deal with, right? Are these numbers? Can you deal with these numbers still? Is 5 to the 42 like a nice number? No.
No.
I think something you gotta try. Like, the thing is, you have to be willing to experiment. Because like, if you like, the reason I'm not telling you if it's correct or not is because the point of problem solving is to experiment with things. So you gotta be fine with like having that uncertainty there. So just like try things, and if they work, they work. If not, you can try something else. Mark, can you represent this as a solution? Like, how would you explain that as a solution?
Or like a worded.
Yeah, with words and like explain the steps. Each step. Yeah. So what sort of ideas have you had so far?
Let's try. Like doing one number. Yep, that didn't because
No, that's fair. Good try, but it is too big, right? So
Yep.
Yeah, I think I'll give you a hint. You have to keep them in combination. There's an interaction between the two numbers that's important here. So you can't, like, each of them individually will never get a nice number. But perhaps try 5 to the 42 if you can break it down a bit more. Might observe something.
Can you like literally subtract? Can I do that?
No, not quite. That's not a power law. Like if, for example, 3 squared plus 4 squared, that's 9 plus 16, that's 25. But if 3 plus 4 is 7 squared, it's 49. So it doesn't quite hold. So again, residues are pretty small, but you can always try something small because again, we don't know what the answer is. You gotta try all like the possibilities we've seen so far. So all the possibilities we've seen so far is breaking down to the residue. But then if that doesn't work, we might go down even more to the negative one, the negative number closest to it. See if that gives us some insight, some connections. It's whole number negative itself. It's not negative 2. Negative 2 is negative to the power of 42. So you put this in brackets. Okay. Do you know why that? Because like you're making like 5 negative 2. So that's negative like 42 and negative 2 is being multiplied together. It's not negative up to the 42. So that's why. Did you do that? Oh, that. This bit. Negative 2 itself. No, not like that. That just doesn't check. Negative 2. That means you're taking negative 2 to the power. Cool. That might help you a bit. But that changes the answer. Your answer's correct, but I think the logic might be slightly off.
Oh, what would it be? Negative. Would it be 7? Would it still be 7? 5 take away 7 would be negative 5. Take away 7.
What do you think?
Negative. So
Like 5 take away 7 is 7 take away
5 take away
5
7.
take away 7. So I think we've done the other one.
When 5 take away 7 equal negative 2.
So that's negative 2 to the power of 42.
Do I need to put in brackets?
Yeah.
Okay.
Unless like you did that step twice. Like thing is, your answer's right, but I just want to make sure you understood the logic. Was this step you going to negative 2 and then realizing when you take negative 2 to the power of 42, the negative cancels?
Oh yeah.
Did you do all the steps in one?
I kind of like. I didn't really notice that part, but I just thought that it would cancel.
Yeah, I think you had an intuition there, which is right, but I think to be exact, it's better. So I think you should split those two steps out into 2.
What should?
Also, when these two subtract, they just cancel, so you just get like it's just 0. It's not 0 to the 42. Like it's not wrong because 0 is 0 to the 42, but you just have two numbers subtracting to 0.
For this step, for the canceling out, what should I?
Well, there's still a minus here because you subtract. So sorry, minus outside as well. It's 2 to the 42 minus negative 2 to the 42. No. You're right to put in bracket, but you have another minus outside.
Alright.
Yeah. So this is subtraction, right? But then you also make the 5 become a negative 2.
Oh yeah, I see that. Would 5 to the power of 42 be in brackets itself, or would the 42 be outside?
42 is outside the brackets. So it's minus 5, is it? No. Key observation you need to make here. Again, I'm not going to make you calculate this. So you both actually have the same step. Make a key observation here. It's very powerful. What's negative 2 to the 42? How do these two relate to each other? About that same sort of base without the, if you ignore the negatives. How does that matter? What can do? This one is pretty tricky. You can try both. These are both a bit different. Since you've already ahead, and if you want to take a little bit of breather, once you finish, try one, you can move. One of these two.
Would I just go straight to that step? Or
Why?
is there?
What's the reason you can go straight to it? Can you go there? That's the reason you gotta like find the connection. We have a negative number being taken to an even power. What does that tell you guys? Take a negative number to the even power. The negatives will cancel. So negative 2 to the 42 is the exact same as positive 2 to the 42, right? Do you agree? I've taken the residue. Subtract the 7 from both because it's congruent. But then the key observation here is this. Negative 2 to the 42 is the same as 2 to the 42. Why? Negative number to an even power. And these two are just subtracting the same number twice. What do you end up with? Same. And that's your answer. But actually, there's also a hidden concept you might have even, like you did even without thinking, which is to even do this. Because look, the exponentiation property, like the power property, only works in isolation, right? A to the k is congruent to b to the k. So you actually, like when you go from like, when there's subtraction involved, you're also using like the addition / subtraction property as well, which basically says you can replace a plus c with two numbers congruent to it. So I'm replacing 9 to the 42 with 2 to the 42 because they're congruent. It's combining the subtraction / addition property with the exponentiation property as well. So it's combining both properties there. So in a solution, it might be good to identify that property as well. Cool. Okay. We'll move on now. Yeah, I know you started this question, but it's all right if you haven't made much progress. Like even attempting it's worth it, right? Yeah, because by the way, the holiday homework will be a bunch of questions on here. I think you did a lot of questions. Did you do most of them?
Yeah.
Yeah. Even still, I think redoing them might be worth it because it's probably a lot of insights you learned here today because these are pretty hard questions. But I'll take a look at your homework, and if you've done most of them really well, I'll set some different questions for you as well. Cool. If not, like, I'm sure there's plenty of learning to be made in just this set. There's a lot of questions. Yeah. Also, the solution method is long, so you don't need to do it for everything. Just do it for a concept you feel unfamiliar with, and you feel a lot more familiar afterwards. Okay, let's move on. I'll show the solution for 12.29 basically if you want. Don't have time to go through this fully today. But the key idea is if A is congruent to 19 mod 30, it's like what numbers are congruent to 19 mod 30? 19, what else?
49.
49. You can keep adding 30. That property definition, which is difference is multiple of n, you can use that to generate congruent numbers pretty easily. So you can probably notice a pattern, which is that the last digit is always
9.
9. So what do you think it's going to be mod 10? It's going to be congruent to something mod 10. Because again, look, the question asks us to switch to mod 10, right? That's the tricky bit, right? We've never switched a mod before. We've always stuck with the same mod again and again. So A is congruent to what mod 10? What is your guess as to what it could be? Last digit's 9, so it's going to be 9 mod 10, right? Just by looking at it. By observation. This is not a formal justification, but would you agree with my observation there? Last digit's 9 for all of them. You think it's going to stay at 9? What do you get? What do you think? The last digit's going to stay at 9 or no?
30.
Yeah, you're adding 30s. 30 is a multiple of 10. So yeah, it's going to stay at 9. So I think this is not a proper justification. We can reasonably assume A is 9 mod 10. If A is 9 mod 10, what's 3A?
I mean, A is
In mod 10. We switch to mod 10 now. We're basically done.
27.
Yeah, you just add 3 times. You replace A with 9. It's like part of the multiplication property. We don't replace both numbers. We just replace the A with the 9. We can keep this 3 as it is because it's already pretty small. 3 times 9 is 27 mod 10, which is just going to be, you break it down, it's 7. Exactly. So does that make sense? I think here I didn't fully justify things though. But to fully justify things was where you need the algebraic definition. If A is congruent to 19 mod 30, right? What that tells you is A minus 19 is what? This is the proof for this step. A minus 19 is 30 times some whole number. Call it K. Algebraic definition, right? A minus 19 is 30 times some whole number, 30K. So this is where the algebraic definition is really important for the harder questions. It's where it really is powerful. And look at this. A minus 19 is also equal to 30 is what? A multiple of 10. 10 times 3K. Distributive property, took out the 10. So that means A minus 19 is a multiple of 10, which means that A is congruent to 19 mod what?
10.
Mod 10. Not just mod 30, mod 10 as well, because of this property we notice. We use the algebraic definition. To start with, A is congruent to 19 mod 30. Look at this sequence. Convert it to the algebraic definition, right? Then we do a bit of manipulation there. We just took out the 10. factorize things, like so algebra. Then we convert the algebraic definition back to the modular definition. That's the proof that it works. And 19 mod 10 is what? 9 mod 10. And then your steps from there is the same as here. So if you want to prove these things, this is where the algebraic definition comes in. And that's why you can, like, by trying to come up with a solution and like asking why is this true, right? Like I only came up with this by asking why this is true. And like you probably won't come up with this easily immediately on the first attempt. What you can do is by asking why here, you can get ChatGPT or something to solve this, and then you can observe the key things from here. They'll probably spit out this. This is not a too complicated thing for it. So that's when you can like asking why in these each individual steps. Because look, when you're doing the solution, you need to explain the step. And when you explain the step, you'll naturally ask, why does this work? And when you do that, you can find these sort of extra things. Cool. Okay, any questions about that? All right, if not, we'll take a 5-minute break. And afterwards, we'll go to quadratics. Well, we'll just do a basic start of it. And then next term, we'll take it more seriously. By the way, are you guys cold? Sure. I just forgot to put the heater on earlier today. Put it on.
That's fine.
Sure.
Yeah, I mean, I'm
Are you guys? Yeah, all good. Sure. Cool. Let's continue. Right. But oh, by the way, I just wanted to say like the reason like that I'm emphasizing the proofs a bit, like even though they're a bit tricky, is when you understand like the thing from a more definition point of view instead of just memorizing formulas, you can use the knowledge a lot more, right? Like, for example, I never taught you to switch from here to here. But if you use the definitions, that switch becomes possible, right? So think about it from a definition perspective as well, whenever things get tricky. So when the question gets hard, go back to first principles, like what's the definition, algebraic, that sort of thing. That will help you out a lot. Cool. Okay. Anyway, let's get to quadratics though. Pretty excited because quadratics is probably the most important topic you'll learn this year in this class, and probably one of the most important topics in all of high school. Right? If you get quadratics, then oh, it's already used. 2. So where did quadratics? Let's again. This week's more about getting our brain used to the idea of quadratics. So, like, here's the thing: it's fine to feel a lot more like confusion this week than you would in like you would have for the last couple of weeks, because we were wrapping up modular arithmetic last 2 weeks, right? So you probably already at a decent level of mastery towards the middle, and so like you wouldn't have as much doubts. Maybe not for you because you came last week, but this week, because it's a new topic, all of you will have more doubts, and that's normal because you're meant to have more doubts, because I'll only cover a certain bit of the topic, so you'll have more questions about the other parts, and that's okay to have. And if you can answer them early, that's great. If not, don't feel too frustrated. What I mean by answer it early is like when you do the homework, try to like find learning gaps and fix them. But if not, just like it's okay is the thing I'm trying to say. It's like it's okay to feel more doubt early on in the process. But think about when you learn modular arithmetic. I don't know, 4 weeks back, was it? Or for you last week? I think 3 weeks back, right? It felt so foreign initially, right? Now the concepts are a lot more like natural to you, right? That's the thing, you'll feel it. And the reason I'm saying that is because this is probably the biggest topic we'll cover. So you'll feel like probably even more so here. Or you might not. If so, that's great. I'm not exactly sure. You know, we all have different preferences. So you might find this topic easy somehow. And that could be the case. And I'm saying general things, so they might not apply to everything, all of you. But either way, let's get started. But the point is, be okay with like having questions. You ask them, right? You're meant to have questions early on. But quadratics. Before I even talk about what quadratics are, let's talk about linear equations. That's where we left off last week, algebra. Nathika, have you done linear equations? Okay, so you're going to be chilling with that part. So, because this really is a map that led to quadratics. So you initially started with linear equations, you know, equations like x plus 3 is 2x plus 1. And you can solve this pretty easy. Right? You end up with x, or you can bring x to one side and you get minus x from both sides. You get 3 is x plus 1. Minus 1 from both sides, you get 2 is x. So, you know, this is a pretty standard process you've probably gotten used to, isolating the x, isolating the constant. And if there is a coefficient here, you divide it, but luckily there wasn't, so you just finish there. But is this process familiar to you? Yeah, you've probably done this countless amounts of time. But now we get to quadratics. And well, I'll give you sort of the history of it. And the history of it goes back probably like a couple thousand years, just like most maths do, back to in the ancient Greeks, those guys that did Pythagoras theorem. Pythagoras is one of the ancient Greeks, right? So they did a lot of maths. So, and in fact, quadratics was motivated by a geometry problem as well, just like Pythagoras. So actually, one of the problems that motivated linear equations was actually area. Think about this problem. The area of like a plot of land, it's 48 meters squared. Then I give you that one side is 6 meters. And then I ask you what's the length of the other side. 8, right? But under the hood, it's a linear equation, right? 6 times x is 48. It's a very easy one, so you can do it in your head. But it's a linear equation. And if you solve this, you get x is 8. If you divide both sides by 6. Now you don't need to do it with the linear equation because it is very, very easy, but when the number gets, a bit uglier, so if I say this is 53, this is 11, and I ask you what x is, what's the answer? Let's say 11x is 53, right? That's the area formula. And that means x is? Yeah, it's a fraction 53 over 11. You might still be able to do it in your head, but it's still, it's probably a bit easier now with the equation. So it's similarly, there's another problem. So this problem led to linear equations. But another very similar problem led to a quadratic equation. By the way, I haven't even told you what quadratics are yet, so don't worry about that. We'll get to that. If I told you that this is 48 meters, and I told you that this side, well, this is actually AB, AC, D. If I told you AB is 8 meters shorter than AC, what are the sides of this rectangle?
12 and 4.
12 and 4, right? I'm sure you've done like number puzzles, guessing and checking. And you've seen the factors, you can figure it out. So 4 and 12. But happening under the hood is what? Let one of the sides be x.
X plus 4 and 8.
Plus 8.
Was it? Yeah.
It's 8 meters shorter. So yeah. Let the shorter side be x. You get x times x plus 8 equals 48. Because this side is x, this side is x plus 8. Cool. And you get this expanded. X times x is x squared. X times 8 is 8x equals 48. All of a sudden, we got this new object we haven't seen much. It's x squared. And that really messes things up. Because finding this equation is actually quite hard. But that's where our study begins. We got to figure out how to solve this. But we saw that we could do it without the equation, right? But I'll show you where you need the equation. Give you a different example. Exact same problem, just change the numbers up. Let's say the sides are 36, and I say that AB is 3 meters shorter than AC. Can you find the answer? Exact same problem, right? Just change the numbers up.
Is it a whole number or is it gonna have decimals?
Decimals. That's the thing. It's all of a sudden, even though the actual numbers in the problem itself are whole numbers, the answer is decimals. And actually, it's not even a fraction. It's not rational. Like you can't represent it as like a basic fraction. That's probably the crazy bit. Is if you look at all the factor pairs of 36, 136, 218, 312, 49. I'm guessing this was the ones you were checking in your head, right? None of them worked. None of them have a difference of 3. So this actually means this problem that has whole number like values, right? The area is 36, the difference is 3. Leads us to numbers that aren't whole numbers as your answer. In fact, not even whole numbers, not even rational. So like here, we got a non-whole number answer in the linear case, but it's still rational, right? Still a fraction of whole numbers. But the answer to this one's actually, let me solve it and tell you. Set up the equation. X plus 3, 3 meters longer. X times x plus 3 is 36. Expand, x squared plus what? 3x. Cool, it's 36. And from here, I'm going to sound like gibberish, I'll be honest, because you haven't learned this yet. But you can solve this quadratic in a few ways. You first bring 36 to the left side, minus 36 from both sides. And then you can use there's a formula for this quadratic.
Only do that in quadratics, like the minus what it equals.
You can do it for anything. It's just, well, you probably don't have you probably don't see the reason for it, right? All I'm doing is subtracting 36 from both sides. And that's a valid operation, right, in terms of equations. But you're probably confused, like, why is this guy doing this, right? Like, why is he subtracting? Like, there's 36 nice, this is positive, you made it negative, what's the point? Because this method, first method's called completing the square. Probably confused. It's okay. It's the first method to solve it. Oh, that's pretty ugly. Then I can solve it from here. It's a square. Square root both sides. Pretend everything worked. Pretend everything makes sense till here. Ignore the logic till here. Pretend you're just looking at this. Square root both sides. The x plus 3 over 2 is like square root of this thing. I mean plus or minus. Because you're squaring negative, still get the same. The negative cancels. Get this ugly thing. That's your answer. Very simple problem. All whole numbers.
It was actually all in my head. I just
Yeah.
didn't tell you.
All whole numbers in the thing. But it ends up being this disgusting thing. That's why guessing and checking stops working. Can you guess and check this? Would you check for negative 3 over 2 plus root 153 over 4 next time?
I won't be bothered to, but
But you got to check all the roots.
Yeah.
Root 152, 151 till you get here. Right? Now, do you see, like, we need a way to solve this equation because guessing and checking just doesn't work. Unless you somehow, like, thinking sets, which I don't know anyone that's currently done that. But no one, so because of that, because we think in whole numbers, we can't think in sets. you can let me know how to think in thirds. We have to figure out this equation first. And that's what our entire topic will be focused on. Build up to this. We're not going to solve this today. This is pretty hard. We'll start with some simpler quadratics. We'll build up to things like this. Cool? I'm just laying out the context. But look at this thing. We had a problem with just whole numbers. And we ended up needing surds. That's why we need to study this in a bit more depth than, because otherwise you would have been like, oh, well, why do I need quadratics? I can just solve this in my head, right? But not the general problem. You can solve very nice problems that I give you with nice numbers. But if I cook up the numbers to make it bad, solving it in your head's impossible. This is not saying like I'm not saying like you're bad at doing mental maths. I'm saying no one can do it. It's a problem no one can do in the head, right? So that's the motivation for quadratics. We need to figure this equation out somehow. So a quadratic, now I'll define the quadratic. A quadratic is an equation of this form. Ax squared plus bx plus c equals 0. Very similar to a linear equation. Linear equation is just ax plus b equals 0. Right? Every linear equation you can convert to this. Even this, you can convert to this form. Right? You just bring all the x's to this side. You get x plus 1 is 3. Minus 3 from both sides. You get x minus 2 equals 0. That's this form. All linear equations can be brought to this form. All you're doing is adding this squared term. Does that make sense? So all the quadratics is adding this square term. By the way, is it confusing like the notation I've used? I've used a and b like in places that don't match, like that. It's just general like a and b are placeholder values. They don't mean anything. A and b could be anything, is what that means. Of course, if a is 0 here, it's just linear, so you probably won't see a is 0, but you'll see every other number of a basically. So an example of a quadratic would be x squared plus 2x plus 1. Quadratic equation would be this equals something, maybe 0, maybe 10. But that is the starting point so far. Cool. All right. What else? So let's start with some very basic quadratics. Once you can probably solve already without any new knowledge. I gave you a quadratic like this. X squared is 9. What's the answer to this?
3.
Is that all the answers? 3 is an answer, I agree. 3 squared is 9. But it's not saying what's the square root of 9. It's asking what number squared gives you 9. Don't confuse square roots with squaring. They're sort of reverse, but they're not exactly reverse of each other. Is there another number that when you square it equals 3?
Equals 3.
Sorry, it equals 9.
Like a whole number.
Any number, but the number will be a whole number.
Or -3.
-3, yeah. Plus or minus 3. That's a quick shorthand way to write it. It means both numbers, both plus 3 and minus 3 are answers. Cool. So this is pretty easy. I'll give you slight variations of this for you to do on your own. First one would be x squared minus 25 equals 0. You have 3x squared minus 48 equals 0. Which equals b is changed. This is a and b. Doing guess and check, you can solve this like with the equation principles. You can try guess and check after. So all of these can be solved with the equation principles fairly easily. Done pretty well. Very good job. Yeah. Yeah. Why did this explain that to the next? Right. Okay.
I got fucked, but I'm still trying to work out how, like, not just guess.
Oh, for A.
Yeah, like
Oh yeah.
do it like the equation.
I mean, A is pretty much it's just one algebraic step, and you get. But the thing is, once you get to here, like this form, it's like you're guessing and checking, or not guessing and checking. It's square root, basically, right?
Yes.
Plus or minus square root. Can you get to this form from here? Is what it's asking.
Oh, is that what it's asking for? Like,
Well, that's what like the algebraic working would be. It's all the algebraic working would be. Because once you get there, it's like some number squared is something. And then you work from there. Because like A, I'm sure it's like, but did you just like sub numbers in to get A?
I just kind of knew A,
Oh, you just sort
like
of,
off the top of my head.
yeah, it's immediately came to you.
What would it be like? X squared equals 25.
So you have some number squared is 25. Your brain probably like did that step without even thinking.
Yeah.
That's why you got the answer. But it's good to set that up because for B, looking at it immediately, you probably won't get the answer. My hint for you is to treat it like a linear equation. What makes this easy is the fact that there's no x term. So you can treat the x squared term like a linear term. So you do all the linear principles to this. So that would mean isolating the variable. And on one side, and I putting the constant on the other side. And that sort of thing.
I was in your questions test last Monday, which is probably why.
Yeah,
That's the first thing that came to
yeah, that's good. Yeah, you've done it. You did really well. Your working out looks perfect. I would not change a thing about it. So it's good. A, everyone's done this. I add 25 to both sides. X squared is 25. You get X is
5.
close. And minus 5. Minus 5 squared is still 25.
Oh, yeah.
Yep, something squared equals something. It's going to be equal to this. Sorry, if you have like something squared equals something, you'll get both the positive and negative answers. It's not just the square root. Okay, here's the trick. Linear equations. Think linear equations. What makes this easy quadratics is they're basically linear. So you can bring all the x squareds to one side. So I'm going to subtract x squareds from both sides. Then I add 48 to both sides. Well, you've done the same. You can just bring the x squared from where you're at right now. Like, you don't have to follow the exact order I do. You know how you brought the 48 to the other side? You can just bring the x squared afterwards. It's fine. That's the trick, right? Algebraic manipulation. And then when you divide by 3, x squared is 16. that means x is or negative
Or
4.
negative.
That's a little bit of like a thing to try to sorry, the thing you should try not to forget, which is that the answer always includes a negative. Like you're in right now, I can tell you right now, like, because I felt the exact same when I was first learning quadratics. I see this equation, my head instantly said x is 4. You gotta change that intuition to include the negative as well. Right? So your brain should just tell yourself x squared is 16. No, x is 4. Oh no, wait, it's plus or minus 4. Right? Both are important because that's the thing you gotta work on. Because your brain will sort of not agree with you initially, but it will adjust when you do more problems. Okay, that's about as hard as the basic linear quadratic will get. But and well, look, with the way we solved it, it's basically linear, right? Until the end where we do the square root bit, everything else is linear. Do you think we can use similar techniques like this for other quadratics? Well, we don't know. Let's try, right? I'll give you another quadratic. X squared plus 6x equals 0. I don't have any constants. What should I do?
X.
Oh, like you're adding these together?
Yeah. 6.
Do you think that's a property we're allowed to do? Is like some number squared plus itself 5 cubed? Do you think this? You can only do this like a property if it holds all numbers, right? Is that a property? So like, is 5 squared plus 5 equal 5 cubed? Not quite, right? It's 25 plus 5. 5 cubes like 125, I think. It would work if it's 1. Would it?
Like if x was 1, x squared plus x cubed, because 1 cubed would equal 1.
But 1 squared plus 1 is 2. It's close though. You're pretty close there. I think it's like, I don't know, actually, it's quite, oh, the number so that x squared plus x is x cubed is also a quadratic equation. You know the problem you just said? It's a quadratic equation. You know why? Here you can factor out the x, and you need to find the solution to this quadratic. And that will give you that number you want. It's not a whole number, unfortunately. This is just quadratics appear out of nowhere. This random problem that you wanted to solve ended up being quadratic. Okay, so yeah, unfortunately it doesn't work as a property. And the answer is a bit less than 1. You're very close. 1's very close. It's like a point, maybe 9 something. Maybe other way, it's 1 point something maybe. Yeah, I think it's 1 point, low 1 point something. But x squared plus 6x equals 0. So we can't combine them. We just noticed now. What are some other ideas? Again, it's fine to be wrong. Like this is your first time seeing this. I'm not expecting you guys to like get the answers. Just throw out ideas you have in your mind. We'll go through them and see.
Really try dividing 6 from both sides, but then it would be like 0 divided by 6. So
That's fine. 0 divided by 6. It's not dividing by 0. You're dividing 0 by 6.
2x squared.
Where would you get the 2x squared?
But could you, like the 2x, could you make that? Could you like,
Or x squared and x combined to get 2x squared?
oh, like, yeah.
Is that also a property? We can check with numbers. Put numbers in. 4 squared plus 4. 2 times 4 squared. No, right?
Yeah.
No, so good guess. Again, we learn whether we can try some algebraic shortcuts. I think the key thing is you can't combine these. as much as we'd like to. You have to treat them like they're completely separate from each other, essentially. And you can collect like x squareds together because they're both x squared, like we did here. But as much as we want to, we can't, unfortunately. We're seeing this, right? With counter examples. It's proving us. And that's okay. Like, this is good that you came up with these. Because we slowly build our intuition that we can't combine this. And that's the intuition we're trying to build here. So you can't combine these, I think, is the point. And are you sort of convinced by that now that you tried a few things? So we have to leave them as it is. So we'll try first idea, divide by 6. Because you want to make this simpler, right? Just like, so there's an ugly coefficient. We want to make that go away. And 0 divided by 6, no issue. It's still 0. Great. 6x divided by 6, x. So x squared plus x equals 0. Is that what you think? Is this right? What do you guys think? Yes or no?
No.
If no, why do you think it's wrong? What have I done wrong here? What principle have I violated? Principle of equations is divide or apply the operation to both sides, right? I violated that principle because I applied it here, but on this side, I only applied it to this number, not to the side. So I got to divide the entire thing by 6. So x squared plus 6x over 6. When I do that, I get x squared on 6 plus x equals 0. Now do you think that this is any better than this? It's just about the same, right? Here you have one nice term and one bad term. Here you have one probably slightly worse term and one okay term. Right, so it hasn't gotten better because when we try to make one better, the other will get worse. That's okay. And like again, we're using our linear algebra intuition, right? And the unfortunate thing is, as good as our linear algebra intuition is, and you will use it a lot later on. So don't forget the linear algebra intuition, but it doesn't hold up in quadratics. We need a whole new toolkit, essentially. One idea that could work, that seems to work, but actually doesn't. I'll tell you why soon. I thought of this earlier, and it doesn't work exactly, is to divide by, not by 6, divide by x. You divide by x, what do you get? No, you're right, I'm just doing it.
X plus 6 equals 0.
Divided by x is just 0. What type of equation is this? Easy linear as well, so x is -6. You could get solve it like this. But actually, you wouldn't be right. You wouldn't get full marks for this. You've actually missed a solution. Do you know why that is? There's another solution to this. Yeah, we got time. Okay, before we did algebra, let's say like back ages ago, primary school. Do you know one of the biggest rules in maths? You're not allowed to do something. You're not allowed to divide by. Two. You're not allowed to divide by 2. Oh, no. I'm just fidgeting. What number are you not allowed to divide by? I think you mentioned it earlier. 0. You're not allowed to divide by 0. Now you're asking, I divide by x, not by 0. So why do I need to be concerned? But x is a variable. It can be any number. So when x is 0, I can't do this division. Right? Would you agree? So that means this only works for all, this works for almost every case, but except one case where x is 0. So x is -6 is the solution if we ignore 0. But 0 is a possible value, so we're gonna try it as well. So we can get all the answers just by trying x is 0. We sub x is 0 into this. Is that an answer? If I sub x is 0, does the equation hold? Yeah, 0 plus 0 is 0. 0 equals 0. Like remember, a solution to an equation means a number that I can sub in so that like both sides of the equation are equal. If I sub x is 0, I get 0 plus 0 is 0. So that's valid. So whenever you divide by x, just have a separate, on a separate side, check x equals 0. Because you're not allowed to divide by 0. So like from here, like literally the rest of the equation, not valid if x is 0. So you have to consider x equals 0 separately. Makes sense? So what you can do is you can just divide by x, but then consider x equals 0 separately. Cool. So a good example of this would be, I'm going to give you some practice questions. X squared plus 6x. Oh, that's the same question. X squared equals 9x. A part B is 2x squared minus 8x equals 4x. Oh, no, 3x squared. Yeah, solve these two. X squared equals 9x and 3x squared minus 8x equals 7x. Check for C. You check the valid case. What, when you divide by x, what sort of things are you ignoring? The fact, maybe. See, yeah. It doesn't hold up, like you can't divide by 0, so we consider that completely separate. Well, what's your answer? A? 3. Oh, did you square root both sides?
Yeah.
But then you square root 9x, it's not 3x, it's like 3 root. Like you can't take the square root applies to x as well. So you don't just square root the 9, square root the x as well. That becomes big. I'll show you what. X squared is 9x. You wanted square root, right? X, you probably did plus or minus maybe, even if you didn't. Okay. 3, but then you said 3x. But the square root applied to the entirety of this thing. So the square root applies to the x as well. You take out the 9 because root 9 is 3, but the x will still stay inside the square root. So you get x equals plus or minus 3 root x. Now this equation is even uglier than before because we got x on both sides. We need to get a whole number answer, right? You can't have x in the answer. So this actually got worse by square rooting. So we can't square root in this case. The only reason we could square root before is because like it's just x squared with another whole number with a constant. But here you have two x terms, the x squared and the linear. That's the problem. So you can't square root. When you square root, the linear term will get ugly. And it will got even messier than before. Like square root equations are a lot harder. This one. Square root is plus or minus. Everything looks right. So what do you get plus or minus 5? It's 5. If you sub that in, you get electrification. You're subbing in negative. Are you checking that? All right. Yeah. So, and that makes sense because like x plus or minus comes when it's x squared equals. It's just x equals. So it just. So
Kind of confused what I would do.
So you just need to check because literally you can divide by x with every single number except 0. All you gotta do is just check. Oh, okay. Let me check if x equals 0 is the solution.
So
Yeah.
I need to write.
You just say check x equals 0 and then you sub x is like sub it. When you check for one number, it's just sub it. The reason we don't do that in general is because, well, there's infinitely many numbers. So guessing and checking won't work in general, but when the number of numbers we need to check is just one, we can do that.
What to do now?
Okay. So for A, it's not the answer. Because you want to find x as a whole number or something, sorry, as like some constant or something to check. Find x in your answer. You want to find x.
Oh yeah, but be nine.
You know.
Yeah.
Is that the only answer?
Oh, that's negative nine.
Check sub it in. That's negative 9. If you square x, if you square negative 9, what's that?
81.
If you do 9 times, if you sub negative 9 here, what do you get?
Negative 9x.
Sub x is negative 9. To like. No, it's not negative 9x. Like, I mean, sub x is negative 9. Replace x with negative 9.
Oh yeah.
Yep. So are they equal? So it's not a valid answer, right?
Just positive. Right?
Yes, but there's also another answer. Okay, let's go through this. So here's the thing, like you gotta try this some of these new ideas that aren't very intuitive right now. At least if you haven't done much quadratics, right? Thing is, they will be intuitive like next time. You come to class when you've done your homework, they'll be like, oh, this is easy peasy. But for now, it's gonna feel a bit weird. So the key thing is because x is a factor of both, that's the observation. The key observation is x is a factor of both. You have x on the left side and the right side, you can divide by x. When you do that, you get x squared divided by x is x. 9x divided by x, 9. So you immediately get your answer, x is 9. But is that the only answer? What number when I divide by x, what number is that ignoring? 0. Why? You're not allowed to divide by 0. So I gotta check in case, just in case x equals 0 is an answer. Because this will miss that. You divide by 0 if x is 0, right? And dividing by 0 actually messes things up. A lot of times people prove things in maths, but then somewhere along the way they're divided by 0. Like technically I think I can prove 1 equals 2 by accidentally having some division by 0 somewhere. I'm going to show you how 1 equals 2, which is obviously false, not true. But you can do it algebraically. And then there's a mistake, of course, but it's a hard to spot mistake. If 1 is 2, right? Oh no. What's the thing? Wait, let me check online. I forgot the exact one. Oh yeah, this is the proof. You have like let's say you have a equals b, right? Just two random numbers being equal. That's normal thing to happen. Happens all the time. If they're equal, let's say I times this side by a. I can also times this side by a. I get a squared is ab, right? Would you agree? Oh yeah. And then I can minus b squared from both sides. Cool. Just done this. Everything's perfectly normal so far. And then we get, can you factorize this? Anyone know the trick to factorize things like this? You guys tried it before?
Take away b, like in brackets square.
Not quite.
Well,
The one you tried? Remember when we did modular arithmetic? It's some property we used? It's the exact same property. The difference of perfect squares.
A take away b brackets.
Maybe a bit tricky for you because I don't think you've seen this before. But the way it basically it works is that these two are this is a squared minus b times b is minus b squared, right? But the other two terms, which is this bit and this bit, they cancel. A times b minus b times a, they cancel. You just end up with the yellow terms being the ones that actually show up. That's why they're equal. And then here, what can you factor out? Common factor is b. You take out b, end up with a minus b. And then, look, I have the same thing here. Let me divide both sides by that because they're like identical. So divide both sides by a minus b, or also known as canceling, right? When you say canceling, you're dividing. And you end up with a plus b equals b. But we also know that a equals b, right? That's our original statement. So we can replace a with b. That means 2b equals b. Then I divide by b. Divide both sides by b. 2b divided by b is 2. b divided by b is 1. All of a sudden, I have 2 is 1, and maths breaks, right? But there's a lot of issues here. The issue is actually here in this step. You divide it by a minus b. Why does that not work? Because a minus b is equal to 0 because a and b are the same number. You subtract them together, you get 0. So you divide it by 0 at some point. And that broke everything. And that was the issue. Cool. Anyway, that's not relevant to what we're doing. But I'm trying to say dividing by 0 is bad. That's why you always gotta consider the case. So like what you do here is, well, you could just sort of consider the case. This is when b is not 0. So when a is not b, you could sort of say a minus b is not 0. That means a is not b. But that can't be true, right? Because we know that a is b. So this breaks down. That's why same thing here. You got to consider the case when it's not 0. Does that make sense? So you've got x is 9 when x is not 0, but then I've just ignored one little number, which is 0. Just check. X equals 0. And when you check that, you will find that it is an answer, right? 0 squared equals 9 times 0. That's true. 0 is not 0. So you've got your answer there. Cool. And that's how you approach these questions. Divide by x. And for this one, for b, very similar. You can either subtract by 7x on both sides or add 8x to both sides. Both work. Get to this form, divide by x, and you keep going. Right? Any questions? So that's the general type of question we've seen so far. What are your thoughts on quadratics so far? Bit weird, right? The way you approach them. And I'll be honest, it's gonna get even weirder next time, sorry. But once you're done with this, you'll have a whole new perspective on solving equations. You'll find linear to be like, oh, so easy. I'm wasting my time doing this. But this is probably if you like, focus and do all the work for this, the reward's really good, right? This is the most important topic in early high school maths, I'd say. When you get to like VCE level, probably calculus and stuff. But all the way till I'd say 9, end of year 9, quadratics is like the most important thing. It sets the foundation for everything. Cool. Okay. But even this is a very, very, very special quadratic. Why? All of this, like these quadratics that I've shown you, I'm missing what? What's missing in this? These quadratics. This is missing the constant, right? There's no constant. If there was a constant, can you divide by x? Why not? Let's say it's 3x squared minus 8x equals 7. If I divide by x, what happens? This is fine here, but then 7 divided by x is... You can do it, it just becomes ugly. 7 over x. So you made it even uglier than it was before. So we'll figure out how to solve these sort of things next term. But that's it for today. Call it there. But all I want you to be able to do is solve these very, very, very special quadratics. And they are almost linear. I call them almost linear quadratics. But next week we'll learn how to deal with things that are further away from linear. Cool. All right. Let's call it there. Do you guys have any final questions? No. In that case, do you want to do Kahoot? Yep. Okay. Kahoot. And again, no class for 2 weeks. We start again on 20th of June.
July.
Yeah, July, sorry. Yes. Okay, what do you guys want to do? Show this. Any topics? Try to look for some, but I'm not up to date with a lot of these, whatever these things are. Do you guys do Kahoots in school often?
Times last week.
Oh, because last week.
Yeah.
Uh,
So we're like finishing all our tests and stuff, and the teachers are like, do you want to finish up with the Kahoot?
I haven't played like or trivia. Let's see what there are. Anything? Oh, it's French. Can you please speak the language? Famous landmarks. Yeah. Let me check if it's hard or not. Oh, it's not naming them. That's annoying. Like ask facts about the landmark. They tell you the name and they ask, oh, what is it used for? Or something. Let's do something else. I'll get a different landmarks quiz. There's a quiz called Famous Landmarks in English-Speaking Countries. Ignoring the ones in outside of the English-speaking countries. Okay, I think I've got one. Oh, never mind. It's also annoying. Oh, it's a 20 question. We'll finish with a big one to end the term. This one looks good.